Okay, for what we have in terms of first order differential equations that we have as a common application in science, especially going back to classical physics, we have Newton's law of cooling, and we have various forms upon which that law can be expressed mathematically. And for what I have with this particular equation, so I have change of uppercase t with respect to that of lowercase t is equal to k times the quantity of t minus t sub alpha. And for what the letters are referring to, okay, we have with the dependent variable, okay, we have the uppercase t, that is going to be the core temperature. Lowercase t is the independent variable, which is going to be in reference to time. And for the T sub alpha, okay, that is going to be the temperature of the surroundings. And that can also be referred to as the ambient temperature. And with the core temperature as the dependent variable, if we look at expressing in terms of the temperature T, okay, so what we can do is look at separating the variables. Okay, so what I can do here is I can collect together what I have in terms of the temperature T, and also separating from the time variable lowercase t. Okay, so what I'm going to do here is I'm going to simultaneously divide by the difference between the core temperature and the ambient or surrounding temperature, and multiply by the differential dt. Okay, so upon separating, okay, so you have dt all over t minus t sub alpha is equal to k dt, and separating the variables, we can go ahead and integrate. Okay, so we have, again, for the dependent variable, okay, the expression we have as the reciprocal of what I have in the variable t for temperature. Okay, so antiderivative is going to be a natural logarithm. So I'm going to have the natural logarithm of the absolute value of temperature T minus T sub alpha, and to the right, okay, so I'm integrating over the time T, antiderivative of k dt, that will be kt, and I'll just say that I have plus C, and looking at expressing in terms of the temperature T, so I can free up the absolute value of t minus t sub a upon taking the natural logarithmic base e. Okay, so treating both sides of the equation as powers to which the natural logarithmic base e is going to be raised. All right, so left-hand side, okay, I'm going to end up with the absolute value of t minus t sub a, and to the right, you have e to the kt plus c, and that can be written as e to the kt times e to the c. After a while, these items will become strongly implicit enough where you can just kind of bypass the intermediate reversal of the product property step and just go ahead and write the resulting constant as just a, or whatever variable you choose. So you have the absolute value of t minus t sub a. We'll go ahead and say that is equal to a times e to the kt, and taking care of the absolute value notation. So we have t minus t sub a, and technically have equal to plus or minus a times e to the kt, and you can also, in a manner of speaking, sort of skip this step, but we'll call plus or minus a, just let this be put in terms of a letter. And it could be from any alphabet. I'm just going to, once again, I'm choosing the Greek alphabet, but you could go with the letter C. So here we have t minus t sub a, and we'll say we have is equal to beta times e to the KT and isolating what I have for the core temperature T. So you have at any time T, you have that the core temperature is equal to beta times e to the KT, followed by the addition of the surrounding temperature. So you have T is equal to beta times e to the KT plus T sub alpha. Okay, now let's say that as an application of computing for the core temperature utilizing Newton's law of cooling. Okay, let's say that we have an object to be removed from a furnace with a core temperature of 1000 degrees Fahrenheit, and the object is placed in an area with a surrounding temperature of 50 degrees Fahrenheit. And we have, after removal, we have 10 minutes later that the core temperature of the object has dropped to 700 degrees Fahrenheit. And then we have, in accordance with Newton's law of cooling, just how many minutes it will take after removal from the furnace for the object to end up cooling down to 200 degrees Fahrenheit. Okay, so we have, again, with Newton's law of cooling, and just transferring over. So again, we have with our formula. Okay, so we had the core temperature is equal to, again, the constant beta times e to the KT plus the ambient or surrounding temperature. And just some things we can mention, okay, is that we have initially, okay, and where we have two phases that we have regarding time. Okay, so we have upon removal, okay, just some key items of information. So we have at time 0, you have the temperature of the object to be 1000 degrees Fahrenheit. And we have for the surrounding temperature, okay, that's going to be the ambient temperature. That is going to be at 50 degrees Fahrenheit. And for other items of information, okay, so you have after 10 minutes, you have the temperature to cool down to 700 degrees Fahrenheit. And then we have at the ends, okay, we're looking at the value of the time t, whereupon the object will have cooled down to 200 degrees Fahrenheit. Okay, so just putting things in play. Okay, so we have, again, with our information case, you have at time 0, you have the temperature at 1000 degrees. And applying substitution case. So you have the core temperature at 1000 degrees. And we have equal to beta times e to the k times 0. And the ambient temperature, okay, we're going to have at 50. And what's going to happen here is that now for, you have k times 0 is 0, so, and e to the 0 is going to be 1. And what's going to happen here is that, okay, we're going to have that 1000 is equal to beta plus 50. And taking 50 away from both sides, okay, so we're going to have that beta is going to be equal to 950. So we're now beta at 950. And we have for the equation rewrite so far. So you have that the core temperature is equal to 950 times e to the KT plus 50. Okay. Now again, we have 10 minutes after removal from the furnace, the object has cooled to 700 degrees. Okay, so we can start to pinpoint further how Newton's law of cooling is going to play out. So looking at transferring the next items of information, okay, so the core temperature after 10 minutes is 700. So you got 700 is equal to 950 times E, to the K times 10. Okay, so that is going to be 10K, E to the 10K. You have plus 50, and isolating, okay, ultimately the variable K. Okay, so if I take 50 away from both sides, so I'm going to have 650 is equal to 950 times E to the 10K, and isolating E to the 10K. Okay, so I'm just going to divide by 950. Okay, and once again, I'm looking at solving for K. And what I can do here, notice, okay, we use E to eliminate the presence of natural logarithms. And now I'm going to be going in the other direction. So what I can do here is I can now eliminate the presence of E if I just take the natural logarithm of both sides. And for what I have in the case of the natural logarithm of 650 over 950, okay, it's going to be about like a negative 0.3794. Natural logarithm of E to the 10K, okay, that will go to 10K. And if I divide by 10, okay, we can say thus that, say to about the nearest 4 decimal places, K is going to be about negative 0.0379. So we have in the development, okay, so we start out with Newton's law of cooling, and we solve for the constant beta, which was at 950, and now after 10 minutes, okay, and doing our calculations, we were able to approximate the value for K, and so specifying further the values involved utilizing Newton's law of cooling. Okay, so we now have T is equal to 950 times E to the negative 0.0379 T plus 50. And now we have equipped the capacity to determine how long roughly it's going to take for the object to cool down to 200 degrees Fahrenheit. Okay, so we have with this equation, we now have at 200 degrees Fahrenheit, so you take our equation and substitute 200 for the core temperature. Okay, so we have 200 is equal to 950 times E to the negative 0.0379 T plus 50 and we have taking 50 away from both sides. Say at 150 equal to 950 times E to the negative, once again, 0.0379 T, and dividing by 950. On both sides of the equation. And once again, we can take the natural logarithm of both ends. And so for 150 over 950, okay, we have the natural logarithmic value, okay, somewhere around negative 1.8458. Again, natural logarithm of e to the negative decimal value times t, so we have negative 0.0379t, and dividing this decimal into negative 1.8458, or whatever you have on display in your calculator, we're going to have for t, okay, that's going to be about 48.7. Okay, so for the time, okay, so you have about 48.7 minutes. And you can say that we have between 48 and 49 minutes.